All right. So what we're looking at here, guys, is the different types of measurements and quantities that we might use in physics. Okay. We're also going to look at how we as North Americans view a lot of physical things completely wrong. Okay. The way we describe stuff in our society in terms of physics is just totally wrong. Okay. Let me give you an example. If I was to ask you how far it is to Edmonton, what would you tell me? 3 hours, 4 hours, hopefully not 45 minutes. I don't know how you're doing that. Okay, maybe you have a plane, okay, that I don't know about, but okay. What did all of you tell me? You told me how long it takes to get to Edmonton. What did I ask? I asked how far, but that's how we think, okay? That is how we as North Americans think, okay? Honestly, guys, I've been asking that question of students longer than you've been alive, and I have received the correct answer to that question less than 5 times, okay? That's just how ingrained that thinking is, okay? And I even do it sometimes. I'm a physics teacher. Somebody says, hey, how far is it to Brooks? And I tell them how long it takes, okay? What's wrong with that? It's not how far, and secondly, how long it takes is variable. If road conditions are ideal and I can go the speed limit, it takes this long. If road conditions are bad, it takes longer, but it's always the same distance. Okay, Brooks is always just as far and away from Okotoks as it always is, and Edmonton's always just as far as it is. Okay, that never changes. The amount of time it takes to get there does change, and it's dependent on lots of things. Everyone kind of follow me on that? Okay, so that's one of the things we need to look at. We really describe a lot of things just totally wrong, and we do it just because that's the way we think. Okay. All right, we got to look at the difference between distance, displacement, speed, and velocity. Probably up until this point, you used the words speed and velocity interchangeably, like they meant the same thing. Okay, but they aren't actually the same thing. Right? One is a scalar quantity, and the other is a vector quantity. Okay, and what I mean by scalar and vector is scalar quantities just give a magnitude, that is a size. All right, so when you're driving along the highway, you see the signs that tell you the speed limit. They don't tell you the velocity limit. Ever notice that? It says max speed, right? It never says max velocity, okay? Because it can't tell you that. Velocity not only has a magnitude, but it also has a direction, okay? And there could be turns in the road, okay? So if it actually said like max velocity 100 kilometers per hour north, you could be in trouble. If there's a turn, you can't turn, or you're breaking the law because suddenly you're not going north anymore. Okay, it doesn't make any sense to do that. Okay, so we give the speed because speed doesn't communicate direction, just how fast. Okay, velocity is how fast and in what direction. So it's different. Okay, distance and displacement have the same relationship. Distance is scalar. Okay, how far is it to here? It's this many kilometers. Okay, if I'm looking for displacement, I would say it's this many kilometers northwest or left or down or whatever. Okay, I would have to give a direction when I tell someone the displacement. Okay, everyone with me there? So a scalar quantity just has magnitude. A vector quantity has magnitude and direction. Okay. All right, we are also going to be doing some problem solving. So you are going to need to start bringing your calculator to class again, okay? Because there's going to be some math going on here, okay? Today, we'll be starting out with easy math, okay? We're just going to be using this formula, okay? V equals D over T. You are not going to use a triangle lest ye die, okay? You will use the laws of algebra, okay, the rules of algebra to do this. We'll review what those are because I know it's been a while since we used the mole equation, which sets up exactly the same way, okay? So it's not like we don't know how to do this, all right? So we'll be using that formula, and we'll be using this formula. No, I'm not going crazy. Those are different formulas, okay? This one is for scalar quantities. These are arrows. They're physics arrows. They only have one tab on them, okay? These are vectors. They have an arrow over top. That means they have a direction as well. The arrow says this is a vector quantity, right? So when I do give you your formula sheet, you'll see that some of the things on there actually have that arrow over the top. They tell you this is a vector quantity. That's important because the way we solve problems involving vector quantities is different than the way we solve problems that involve scalar quantities. Okay? The math is similar, okay, but the way we set them up is a little bit different. Okay, so for this first formula here, okay, what we're looking at is how to calculate speed. That's what V stands for, okay, speed. We do that by dividing distance by time. Okay, so V equals d over t is speed equals distance divided by time. And that kind of makes sense because speed's units are kilometers per hour or meters per second. It's always a distance divided by a time. Okay, everyone kind of follow me there? This formula here, okay, with the arrows over top, that's how we calculate velocity. So velocity equals displacement divided by time. Okay. Time doesn't have a little arrow over it. It's in both formulas, but it doesn't have an arrow over it. Is time a scalar quantity or a vector quantity? Nope. It's only one or the other. Yeah, time's scalar, unless you know something I don't. Okay? Unless you have like built a time machine and can actually make time go any way other than forward, time is scalar. Okay? As far as we know, time only goes forward. Okay? Oh, there's lots of theories on how time travel can be achieved, but as far as we know, time is scalar. It just passes. Okay? The fourth dimension is time, but we can't seem to manipulate it or make it go any way other than forward, which is why you're never going to get younger. Okay? You're just going to get older. Oh, depressing. Okay. So anyway, time is a scalar quantity. It can only go forwards. You cannot go back in time, at least not in grade 10 physics. Okay. All right. So as we were talking about here before, the way we describe distance in North American society is really messed up. Okay, because we tell people how long it's going to take when they ask us how far. Okay? And that's only good really at getting you hopelessly lost in a trackless environment. Okay, how many people have ever gone like backpacking or orienteering or hiking or anything like that? Okay, like the signage that's on trails in our provincial and national park system is, well, not always very accurate. Okay, but if I'm on this backpacking trip, which I did when I was a much younger man, okay, if I'm here at Seldom Inn Campground and I want to go here to Snake Indian Falls Campground, there's a sign right here on the trail that says Snake Indian Falls Campground, 32 kilometers. Did it give me a vector or a scalar value? Scalar, yeah, okay. It said 32 kilometers. It never told me which direction it's in. What does it assume I'm going to do? Well, on the path, yeah. It's going to assume I'm going to follow the path. It's 32 kilometers along the path, right? This way. It's given me the distance that I will have to travel in order to get from A to B. Now, had the sign said Snake Indian Falls Campground, 26 kilometers at 52 degrees west of north, then it would have given me the green line. Okay, because this would be due north and this would be like 50 degrees west of north, okay? And that would be, the straight shot from one to the other. Signs for good reason don't do that. That path, if I was to go in a straight line, would be A, nearly impossible to follow, and B, filled with all manner of disaster. Okay, look at how many rivers get crossed, and then there's this gray thing. That's a glacier. They're not really safe to walk on all the time. They're full of things called crevasses that you can fall into. Not good. Okay. So yeah, that would not be a good way to go. If I had a helicopter, that would be fine. I would want that one. Okay, I would want them to tell me how far and what direction is it in a straight line, because that's the way I want to go. But I can't walk that way. Okay, and that's how our system of roads works too. Okay, the road signs don't say that Calgary is 25 kilometers north. It just says it's 25 kilometers. It assumes you can follow the road. Okay, sometimes safely and sometimes not so safely. Okay, but it assumes that that's what you're going to do. Does that make sense? So there's a time and a place for each type of measurement. Okay? There's a time and place for scalar measurements, like road signs and trail signs, and there's a time and place for vector ones. Okay? If I'm an airline pilot, I want the short line distance because that's the way I'm going to go. I don't have to worry about going around stuff. Okay? I'll just go over everything. All right, so it's important to realize the difference between distance and displacement. Displacement will tell you how far and in what direction in a straight line, okay, from start to finish. Where distance tells you how far you actually have to go to get from start to finish, or initial to final. Okay. Is that diagram in your notes package? No? Okay. All right, so when we say Calgary's 40 kilometers away, that would be like the city center, okay? 40 kilometers away, we make no reference to which direction Calgary's in. We obviously just get on the road and follow it, okay? And we've made a scalar description of where Calgary is, okay? I've only said how far, not what direction, right? But if I'm giving a vector quantity, then I would say, well, from Okotoks to the city center of Calgary, okay, is along this line. Okay, that would be 13 degrees. Actually, it would be west of north, but whatever. Okay, it's over there. Okay, west of north. Everyone all right with that? Okay, so now I've given a vector description. That's the straight line that you could take to get there, except you'd have to swim across the Bow River, walk through people's houses, like literally through their walls, okay, in order to follow that path. Okay. All right, so scalar quantities, magnitude only, okay, vector quantities, okay, have magnitude and direction. All right, I'm going to erase this and redraw it here to illustrate. Okay, so let's say that I need to go to Wally World to get something. That's what I call Walmart, okay? So I got to go from my house to Walmart, okay? So Walmart's going to be right here. Okay, and my house is going to be over here. Now, unless I live like directly behind Walmart, which I don't, okay, I can't walk in a straight line to Walmart. Okay? There's like a river and people's houses and all kinds of other stuff. So I can't walk in a straight line. So I've got to, follow various roads, right? They don't all go straight. Some of them go straight and then, some of them turn and whatever. And eventually I get to Walmart, okay, eventually, right, by following that. So that's the route I actually take to get there. But in reality, all I've really done is this. Okay, I've walked a lot farther than the shortest route. Right? The shortest route is always a straight line. The problem is it's impossible to follow the straight line in this situation. I don't have a helicopter. Okay? If I did, I wouldn't shop at Walmart. Okay? I'd have somebody else shop at Walmart for me, okay? Because I could afford a helicopter, I could afford a personal shopper too, okay? So anyway, I wouldn't be able to do that. I can't go in a straight line, right? So what I end up doing is following this path. So let's say that in order to walk to Walmart along this path, I have to go 4 kilometers. Okay, everybody all right with that? Let's pick a random number, 4 kilometers. Okay, so it's 4 kilometers from my house to Walmart along whatever path or route I have to take. Let's say that I can walk this route in, now let's say half an hour. Okay, what's my speed? How fast am I walking if I can walk 4 kilometers in a half an hour? If I walk 4 kilometers in a half an hour, how far would I walk in an hour? 8. So my speed is 8 kilometers per hour. Everyone follow what I did there? Okay. All I did was do this formula that we talked about. Speed equals distance divided by time. I took my 4 kilometers and I divided it by a half an hour, and I got 8 kilometers per hour. Okay, everybody all right with that? All right. Well, let's say that that's the route I have to go by, but if I draw like a straight line on Google Maps from my house to Walmart, it says that it's only 2.8 kilometers. And we'll say that that's, I don't know, let's say 40 degrees west of north. Okay, that would be my displacement after I've walked from my house to Walmart. Okay, displacement is the change in position of an object. Not how far the object has gone, that's 4 kilometers, but it's change in position, always along a straight line. So I will have changed my position from home to here by 2.8 kilometers in a direction of 40 degrees west of north. All done? Okay, everyone follow me there? So these two things are talking about the exact same trip. They're just describing it from different points of view. One is what I actually had to do, and the other is what I ended up doing. Okay, if I was talking about a straight line. All right. I want to calculate my velocity from my house to Walmart on this trip. Okay, so that's going to mean take my displacement and divide it by the time. Is the time the same? I mean, it took me a half an hour to get to Walmart, right? I didn't actually follow this line, but it took a half an hour for me to do this. Okay, so the time is still the same. Okay, so I'm going to take my 2.8 kilometers at 40 degrees west of north and divide that by a half an hour. Okay, so that's going to make that 5.6 kilometers per hour at 40 degrees west of north. Okay, it's the same vector, right? My velocity is describing how fast I did the displacement. Right? Therefore, it has to have the same direction. If it doesn't have the same direction, it would be like me saying I went 20 kilometers north, traveling at 100 kilometers an hour west. Can I end up going north by traveling west? No, I can't. Okay, so your velocity and your displacement always have the same direction. Okay, they have to. All right, so now I've looked at the trip to Walmart from both points of view, from a scalar point of view and a vector point of view. Okay, here's where it gets weird. So I get to the doors of Walmart and go, oh, I forgot my wallet. That's never happened to me before, ever. Okay, so I get there, I don't have my wallet. Well, there's no sense going in because I don't like doing that whole like shopping thing. You know, like people go around and look at stuff and then don't buy anything. I find that horribly boring. My wife does it all the time. Okay, I don't understand how she enjoys that. But anyway, that's beside the point. I'm not going in because I don't have any money because I forgot my wallet. So I just turn around and walk home along exactly the same route. What's my distance for the whole trip? If I follow exactly the same route home, how far will I have walked? 8 kilometers. Okay, so the total trip, okay, my total trip, okay, from a scalar point of view here, okay, my total distance is going to be 8 kilometers. And it's going to take me an hour to make that whole trip, right? It took me a half hour to walk there, it took me a half hour to walk back. Everybody okay with that? Is my speed then still 8 kilometers per hour? Yeah, I went 8 kilometers in an hour, okay? Because I did exactly the same thing. Even though I went backwards, I still went 4 kilometers and a half an hour both ways, okay? For a total of 8 kilometers in 1 hour. From a vector point of view, I end up back here, back at my house. What's my displacement for the whole trip? If if I was to draw a line from my initial starting point to my final ending point, would there even be a line? No, because my starting point is my house. And my ending point is also my house. How far have I gone? Nowhere. Okay? From a vector point of view, I ended up back where I started. I have displaced myself exactly 0 meters. Okay? Even though I traveled 8 kilometers from a scalar perspective, from a vector perspective, I didn't go anywhere because I ended up back where I started. Okay? So my total displacement for the whole trip is 0. Okay? Which also means then that my velocity would be also 0. Okay? Remember, velocity is displacement divided by time. And if I come back to where I started, my displacement is 0. And 0 divided by anything is 0. Okay? All right, so that's the difference between scalar and vector. They can describe the same trip, but they do it from different points of view. And as a result, sometimes they look a lot different, even though they're talking about the exact same thing. Okay? Everybody all right with that idea? Yes? No? Okay. All right. We already talked about that one. Okay. So that's just some terminology here. Okay. So in your notes, okay, stuff that's going to be important here in terms of definitions. Okay. We give the distance an object travels. We've used a scalar quantity, 4 kilometers from my house to Walmart. Okay. Displacement of the same trip is 2.8 at 38 degrees north of west. Okay. So we've already kind of done all this stuff here. Okay. But if we're looking at definitions, right? Wow, I'm having trouble making A's today. And object. Okay, distance is how far an object travels. That's it. Okay, doesn't matter what direction, doesn't matter if it's gone back and forth over the same path 20 times. Okay, how far did it go in total? I add every part of it up, regardless of whether it went forward or backward. Okay, it would be like if I ran around the track out here. Okay, if I run around that track 10 times, I've gone 4 kilometers total distance. But if I start and end at the finish line, what's my total displacement? 0. Even though I've run 4 kilometers, I ended up back at the start finish line. Okay? My initial and final positions are the same place. Okay. All right. So that means then that displacement is our change in position. Okay, with direction. Yep. Okay, so if we go back to the running track example, we go back to the running track example. So our running track is like got 2 straights and 2 curves, right? Right, so it looks something like that. So if I start here and I run 2.5 laps, I end up over here. Okay, if I've run 2.5 laps, okay, I've gone 1,000 meters. I've run 1,000 meters. But from a vector point of view, my displacement is from here to there. Even though I ran 1,000 meters, I actually only ended up that far from where I started. Okay, so my distance would be 1,000 meters, but my displacement would be however long and in what direction this line is. Okay, it would probably be about 30 degrees south of east, okay, and it would probably be about 110 meters. Okay, something like that. Okay, everybody all right with that? Okay. Okay, so we talked about this already. Speed and velocity have the same relationship that distance and displacement have. One is scalar, one is vector. So one is concerned with direction, the other is not. Speed is not concerned with direction. Okay, now, rules of algebra. I need you to write these down, and then we're going to go over an example with you. Okay, I know we wrote them down in the, I think we wrote them in the chem unit, but I want you to write them again because we only wrote 2 of them in the chem unit, and there are actually 3. Okay, 3 rules of algebra. Okay, so back in the chem unit, I was recording all that quiet time. If you watch the podcast, fast forward. Okay, so when I'm manipulating an equation, when I need to move something around, okay, the 3 things I need to remember is that if I want to move something, I do the opposite of whatever I'm already doing to it. So if I'm adding it, I would subtract to move it. Okay? If I'm dividing it, I would multiply to move it, etc. Okay. Second thing I have to remember is that if I multiply it on one side, I have to multiply it to the other side. Whatever I do to one side, I do to the other. That's like the golden rule of algebra. Okay. And then the third one has to do with equations that have several parts to it. Okay. So we want to move, okay, when solving for a variable, move what is not attached to that variable first. And that's what I'm going to explain here in just a second. Okay. So a formula that we're going to use fairly often in this unit is the graphing equation. How many people have taken Math 10 already? Okay, so you've taken the y equals mx plus b. Okay, so you've seen this formula before. Y equals m times x plus b. Okay, even if you don't know this equation, I'm just using it as a way to show you the rules. If I want to solve for m, okay, I need to move everything except m over to this side of the equation. Okay, so this is where rule number 3 comes in. I want to move what's not attached to m first. Which is not attached to m, x or b? B. B's not attached, right? X is directly beside it, so it's attached. So I'm going to move b first. Right now, I'm adding b. If I want to move it to the other side, I need to subtract it. All right, so I'm going to subtract b from both sides. So I'll end up with y minus b, so I've subtracted from that side, equals m times x. Can I move x now? All right now I'm multiplying by x, so to move it, I want to divide by x. Done. I've just solved for m. Okay, and I've followed those three rules. I moved what's not attached first. I did the opposite to move things, and when I did that opposite operation, I did it to both sides. Okay, so I followed my three rules of algebra, and I do that every time. Guys, like I teach physics, and I think about these rules every single time I manipulate an equation. Okay, all the time. These three rules got me through university physics. Not so much university math, but university physics. Okay, because university math was calculus, and I didn't get any of that. Okay, like none of it. Anyway, got me through university physics. Just doing algebra, just being able to manipulate simple equations. All right, so now that I've done that, let's look at how we would use this for v equals d over t. So let's say I want to manipulate and solve for d. All right, so if I want to solve for d, what should I move, d or t? I should move t. Yeah. Okay. D is on the top of the equation. If I want to solve for something, it needs to be on the top of an equation. I can't solve for it on the bottom. Right. So I'm going to move t over to this side by multiplying both sides by t. Okay. So I know I just kind of pulled that and moved it over here, but okay. Really, what I did was this. I multiplied both sides by t. That means there's a t on the top and the t on the bottom, so they cancel. And then I multiplied this side by t. So I have t times v equals d. Everybody all right with that? Okay. That's the easy one. We did that in the mole equation, same calculation. Put the marker down. Okay, I want to solve for t. How will I solve for t? Remembering that if I solve for something, it needs to be on the top of an equation, not the bottom. How can I move t to make it on the top of an equation? Yeah, multiply it. Okay, what I just did a minute ago got t to the top of the equation. It also got it to the other side, but it got it on the top. Okay, there's nothing above it anymore. Everybody follow me there? Okay, so now I've got t times v equals d. Yeah, that didn't help me get t by itself, but it helped me get it on top. Can I move v out of the way now? Okay, right now I'm multiplying by v, so to move it I would divide both sides by v. Okay, now I got t equals d over v. All right, all I've done is follow those rules of algebra. Move it to the opposite, do it to both sides. Okay, so really, if I show you kind of the long form of what I did there, okay, it was just this. I multiplied both sides by t, and t came over here, t times v. Right? Then I divided both sides by v. Okay, t equals d over v. All right, that is the extent of the algebra you will have to do for like the next week. Then it'll get a little tougher, because then I'll throw in the acceleration formula, which isn't much tougher. It's got one extra little thing in it. Okay, everybody with me so far? Just takes a little practice. Once you get the hang of it, it's easy peasy. Okay. Oh, I got all the answers on here. That's not good. Okay. Write this one down. We're going to work through it together here. I want to figure out how far a deer will running. How far will a deer running at 15 meters per second travel in 45 seconds? Okay, so write this one down. We're going to go over it together. All right, so similar to how we set up the mole equation questions, okay, the first thing we want to do is read the question and write down the givens. Okay, identify what it is we have. Right, so it's asking me how far a deer will run. How far? What would that be looking for? Distance. Yeah. Okay. If it said how far and in what direction, then it would be asking for displacement. Since it doesn't ask for direction, I'm just looking for plain old d, distance. Okay, so that's what we're looking for. We don't know it. It's running at 15 meters per second. What's that value? Speed. Okay, it's how many meters in a second, right? 15 meters per second, which is like really fast. Okay, that's like the fastest, it's like Usain Bolt sprinting, okay, kind of fast. Okay, so we got t equals 15 meters per, or sorry, I just said t, it's v, sorry, v, it's 15 meters per second, and it asks in 45 seconds. Well, that's time. Okay? And that's how we do it. We have to look at the units to decide what was I given. Okay? If it's in meters per second, kilometers per hour, centimeters per year, okay, it's speed. Not that you'd ever get anything in centimeters per year, but okay. And then if it's anything in seconds, hours, minutes, days, months, it's time. Okay, so I've got V, I've got T, and I'm looking for D, right? So the only formula that we know is this one, V equals D over T, right? And I'm looking to solve for D. So what do I have to do with T? Multiply it over, right? Okay, so T times V will equal D. So I'll take my 45 seconds, multiply that by my 15 meters per second, and that will give me D. Right? You don't have to put the units in when you're showing the calculation. Okay. All right, so 675 meters is how far the deer will run. Okay, so you'd get a mark for writing down your givens. You'd get a mark for picking the correct formula. You'd also get a mark for the manipulation. Sometimes also a mark for plugging in your numbers, and a mark for your answer. Okay, so just like a mole equation question, right? I'm giving you marks for the same things: givens, formula, manipulation, plugging in numbers, and answer. Okay, questions on how that one worked? It's okay with that? Okay. Okay, write that one down and give it a try. Okay, so it's asking us how long it will take. What are we looking for? Time. Yeah, anytime it's asking how long, we're looking for time. Okay, we're crawling 200 meters, so that would be a distance because it's measured in meters or kilometers or whatever. Okay, at a speed of 25 meters per second. So they outright say that the speed is 25. Okay, so I know D and V, I'm looking for T. So V equals D over T, I'm looking for T. T is on the bottom. I can't solve for it if it's on the bottom. I need to move it to the top by multiplying it over to the other side. And then, to get it by itself, I would divide both sides by V. So I end up with T equals D divided by V. So that will be 200 meters divided by our speed, which was 0.25 meters per second. Sorry, I forgot to put the decimal here. Okay, 0.25 meters per second. So I got meters and meters, so the meters are going to cancel and leave me with seconds, which is good because that's what I was looking for, time. Okay, so 200, I think it's going to be 800, right? Yeah, 800. Okay, so that's going to take 800 seconds. It's a long time. Okay. But it's a tortoise. It's not like you're, riding a tortoise. Well, you could, but it wouldn't be very much fun. And it would probably bite you. And they bite pretty hard, apparently. Okay? All right. That making sense? Really, all we're going to work on the next little while, guys, is learning to, get the algebra down, reading the questions, interpreting what they're giving us so that we can make our solutions. Okay. Now, this one's a little bit trickier. It has more than one part. All right, so I want you guys to write this one down. This is one that has a vector part to it. Okay, direction matters in this one. Right, so make sure you make note of the north and the south and stuff in here. Okay, the tips are that if we want to find the average velocity of the bus over the whole trip, what I need to know is the total displacement and the total time. I need to divide those two things in order to get the velocity over the whole trip. But remember, there's two parts to this trip. Okay? So what I need to know is, what did the bus really do? Well, the bus went north and then south, right? It went north and then it came back, but not quite all the way. If I want to find out the velocity of the bus, I need to know its displacement, that is, what's left, how far from its starting position is it, and how long did this whole thing take? If I can find those two things, then I can find its average velocity over the whole trip. So I would suggest writing down the givens for each part of the trip so that you can use them to get the total. Okay, I think that'll take you probably the rest of the day.